Hello, welcome to the seventh lecture for the Mathematics Class 11, Chapter 4, Complex Numbers and Quadratic Equations. So, till now, we have seen how we can have different algebraic operations operating on complex numbers. We also saw how to find the power of the imaginary unit I, like higher power more than 2. And we also saw how we can find the square root of negative real numbers, which actually help the where the unit I, the imaginary unit I, actually comes into play. And we also saw different kind of identities that we can use, and we have also proved how the identities, how the equalities actually are true and how they are valid. And we solved a few examples. So before we move on to the next section of this chapter, we will see some few more, examples related to the algebraic operations. So let's see. Okay. So suppose you are given the expression, you have to solve the following. Okay, so solve 2 plus 2, 3i into minus root 3i upon root 3 plus I root 5 minus root 2 minus 5. Okay. So in this expression, as you can see, you have both the product of two complex numbers as well as the difference of two complex numbers. So this is comparatively an easier kind of a solution, but you can see that you can have different algebraic operations coming into play when you are given some questions like this. So to solve this, we can easily, since you can see in the numerator, this is of the form of a plus b and a, or maybe it's better if I write it in z, because since we are dealing with complex numbers. Okay. So you have kind of, z1 and just, yeah. So you have a plus b ki, okay, and a minus bi. So this, if you remember, we had done, we have seen that you can apply the identity directly to such expressions. So this would be actually in the terms of a square minus b square. Okay. So b square, I square. Now, since I square, is actually, minus, this will actually in turn become a square plus b square. Okay. So in this identity form, we can convert the numerator. So you can directly write it as 2 squared minus root 3 squared pi squared. Okay, and for denominator, you can see that plus root 3 and minus root 3 actually they can cancel each other out, and then you're left with is root 5i plus root 5i. So that you eventually get as root 5i. Okay, so then this becomes 4, and since I square, we can convert it into -1. Okay, so that becomes plus 3, and then you have 2 with 5i. Okay, and then if you write it in terms of, you solve it and you get 5 to root 5i. Now, since I is in the denominator, we want to bring it to the numerator, then you can just add a negative sign and you get this. Okay. So this is an easy example. If you get, a combination of different complex numbers and you are given in this form, you can easily solve it. Then suppose you are given if a plus ib equals to x plus I squared upon x squared plus 1. You have to prove that a squared plus b squared is equals to 1. Okay, so let's first solve that what exactly would be your a plus ib. Okay, so over here you get a quadratic equation, so you kind of simplify. Okay, you expand this quadratic equation, you get x squared plus 2xi plus I squared. Okay, so this you get it in the form of here. So you get x squared, okay, minus 1 plus 2xi. Okay, and then you have x squared plus 1. So now you can actually convert this in the form of a complex number. Okay, so that plus a bi. So therefore, you can write a plus ib is equals to x squared minus 1 upon x squared plus 1, and you have plus 2x upon x squared plus 1. Okay, so you can get it in this form. So over here you can see that a would actually be the real part. Okay, minus 1 x squared plus 1, and b actually corresponds to the imaginary part. Okay, so 2x upon x squared plus 1. Okay, so now if we want to find a square plus b square, so you directly kind of you put this entire term into whole square and this term into whole square. Okay, so what you get is x squared minus 1 upon x squared plus 1, okay, plus 2x upon x squared plus 1 the whole square. Okay, now over here again the denominator is the same, so you put everything together. Okay, so x squared plus 1. You keep this in the whole square. Okay, on the top, you can expand x square minus 1 the whole square over here. So you get that as x raised to 4 minus 2x squared plus 1. And over here, 2x squared will become 4x squared. Okay, and if you simplify it further, what you are remaining with is x square, x raised to 4 minus 2x squared and plus 2x squared. So you have plus 2x squared and plus 1 upon x squared plus 1. Okay. Now, if expand x squared plus 1 also, you will get uh, the same expansion as what you have in numerator, because if you actually expand x squared plus 1, you get x raised to 4 plus 2x squared plus 1. Okay, so hence the numerator and denominator, they cancel each other out, and what you're left with is 1. Okay, so this is hence proved. Okay, so you can see that we used identities, we also used quadratic equations to solve, and we can prove when we are given such expressions. Now let's see another sum which involves operation of quadratic equations. Okay, so suppose you are the question given to you is just one minute. I think I'll have to add one slide here. Yes. Okay. So over here, the question is that k is equals to cos 2 pi by 7 plus I sine 2 pi by 7. Okay. If this is the condition that you're given, what is the quadratic equation whose roots are alpha equals to a plus a squared plus a 4 and beta is equals to a 3 plus a 5 plus a 6. Okay, so alpha and beta are roots of the equation. Okay, and for quadratic equations, as we have even seen before, the quadratic equations, when we write it in terms of such roots, is given as, okay, so we know that x squared minus the sum of the roots as the coefficient of the x plus the product of the roots is equals to 0. Okay, in the form of a quadratic equation. Okay, so we know this. Now we are given the two roots over here. Okay, so we are given alpha and beta. So before we start solving to see what the roots are in more condensed form, as we had if you remember, we had seen that ei theta is equals to cos theta plus sine theta. Either you write I in front of sine, yeah, plus I sine theta. Okay, so this is a rule that we already know. So over here we are getting A is equals to cos 2 pi by 7 plus I sine 2 pi by 7. Okay, so if you if you write it in terms of the power of A, okay, so A7, okay, suppose you write it A7, so you have cos 2 pi by 7 plus I sine 2 pi by 7 is raised to 7. Okay, and since we already know, if you write it in this form, so it kind of becomes over here. If you get that the power actually comes within the your 2 pi by 7. So what you are left with is cos 2 pi, okay, plus I sine 2 pi. Okay, so the 7 and 7 gets cancelled out. Okay, so this is what we get. And since we know that this actually becomes 1, okay, so ei theta in written in this form is also equal to 1. So we can write that a raised to 7 is actually is equals to 1. Okay, this is 1. Since ei theta is equals to 1. Okay, in the form of your exponential and the imaginary angle and I. Okay, so since we now know a raised to 7 is equals to 1. Okay, so this is one of the conditions that we are going to use for the rest of the sum. Okay, so what we get now is, okay, so that's fine. Okay, so now first we find your sum of the roots. Okay, so alpha plus beta. So this we get as I'll just write it over here. So a plus a squared plus a4, and beta is a cube plus a5 plus a6. Okay, so alpha plus beta will then become a squared plus a cube 4 plus a5 plus a6. Okay, so this is what we get. Now, if you take the a outside, you get 1 plus a squared plus a cube plus a4, a raised to 4 plus a raised to 5. Okay, now this is in the form of a series of numbers. Okay, so sum of a series of numbers can be written in terms of a 1 minus r raised to n upon 1 minus r. Okay, so over here, your r is actually, your r is also a over here. Okay, so this you can, it can be reduced in the form of, this entire bracketed part can be reduced to this form. Okay, so you can write this as a. So this is your n is actually 6 over here. Okay, there are 6 terms. Okay, so the number of terms is actually becomes your n. Okay, so you have 6 terms over here. So you can write it in the form of a raised to 6, and this becomes 1 minus a in the denominator. Okay, so now if you get the a inside, you are remaining with a raised to 7 on 1 minus a. Now, since we already know a raised to 7 is equals to 1, okay, so you have a minus 1 upon 1 minus a. Okay, so if you, try to get your numerator and denominator in the, in the same form, then take minus 1 out. So you get 1 minus a and 1 minus a. So this and this gets cancelled out. So what you're remaining is with minus 1. Okay, so this is your sum of the roots. Now for the product of the roots. Okay, so now you have a plus a square plus a4 multiplied by a cube plus a5 plus a6. Okay, so now similarly, how you expand, you open up the brackets and you solve this. So you have a raised to 4 plus a raised to 6 plus a raised to 5 plus a raised to 7 a raised to 8 a raised to 7 plus a raised to 9 plus a raised to 10. Okay, so if you actually expand the, if you multiply each and every term of the second bracket with the entire, with all the terms of the first bracket, when you expand and open up all the brackets, this is what you will get. Now you have 2a raised to 7 over here, so you have 2a raised to 7 plus a raised to 4. If you take out common, you again get a squared plus a raised to 4 plus a raised to 5 plus a raised to 6. Okay, now this is again similar to the previous, when we have used the series, the sum of the terms in the series, same series as can be seen over here. Okay. Okay, so you again get that as 2 raised to 6 to 7 is a raised to 4, and this actually becomes 1 minus 1. So this, you again, since a raised to 7 is equals to 1, you get this as 2. So your alpha into beta, the product of the roots is actually 2. So the final equation that we get, just write it in different color. Okay, so final answer in terms of the quadratic equation itself is actually you have x squared negative of the sum Okay, so the sum of the roots. So you have negative 1 x, and then you have plus the product of the two roots. So you have 2, and that is equals to 0. So you are left with x squared plus x plus 2 is equals to 0. Okay, so this is your final answer over here. So you can see, obviously, we have used, summation of terms in a series, to explain in a better way over here. So you can obviously get questions which is a mixture of two different forms or two different kind of operations. So this is an example of this. Now we will move on to the next section of the complex numbers, where we will see how we can find the modulus and conjugate of a complex number. So modulus, if you in simpler terms, or we have used before too, like finding a mod of any number, okay, whether a positive real number or a negative real number, what it actually does is it removes the sign. Okay, it removes the sign, and it only gives you the understanding, or gives you the value of the magnitude of that number. Okay, now since in a complex number you have the real part, obviously, and you have an imaginary part. Okay, so this imaginary part, there is no, as we have seen, it's a negative number, it's a negative unit. Okay, so to avoid, or to take that out of the to just find the magnitude, or to find the just the value of the complex number, we can find the mod. So in simpler terms, your mod of z. Okay, so mod or modulus of z. Okay, so this is the modulus. Okay, so modulus of the complex number z. Okay, you can write it in this form. Okay, then what you are left with is what how you find it is actually square root of the sum of the squares of the real parts of the complex number. Okay, you can see that we are not including the imaginary unit over here. Okay, so we only deal with the real coefficients, okay, that are there in the complex number. So this is how you find the modulus of a complex number. Okay, so if we take a few examples with respect to finding the modulus. Okay, so if you have, for example, you have 4 plus 5 5. Okay, so we have to find the mod of this. So you have 4 square plus 5 square. Okay, so you have 16 plus 25. Okay, so that you will get 41. Okay, so the mod of the complex number 4 plus 5i, this mod is equals to root of 41. Okay, then for example, if you have mod of 2 root 3 plus I. Okay, so again over here, you, to find the mod, you square your real part, real coefficient of both the parts, real part as well as the imaginary part. So 1 square. So this we will get square root of. Okay, so now 2 square 4 and 3. So this will be actually 12. Okay, so that's actually 4 into 3. And then you have plus 1. So this will be square root of 13. Okay, so you can see that, how modulus can actually give you just the kind of the magnitude of the complex number. Okay, it does not include the I, it omits the I. Okay, now next we will see what is the conjugate of a complex number. Okay, so suppose your Z is equals to A plus IB. So conjugate usually refers to the opposite or kind of like a mirror of an item or a product, okay, of a term. So conjugate is usually that. So as well, when you say like that it's a mirror or it's a conjugate of a term of a complex number, usually that means that some sign has changed in it. Okay, so now if we have Z is equals to A plus IB, the conjugate, which is represented as by putting a bar on top of the complex number, so that is actually A plus IB, the conjugate of this. So over here, you have to note that only the sign of the imaginary part changes. Okay, you can see that sign of the imaginary part is changing, not the real part. Okay, so therefore, Z conjugate of complex number Z is actually A minus IB. Okay, so let's see an example. The example that we have used, you have, example, you have 4 plus 5i. So you find the conjugate of this. So this will be 4 minus 5i. And similarly, if you have 2 root 3 minus I, okay, so this will be 2 root 3 plus I. Okay, so this is how you can find the mod of a complex number. So now if you have, you are given a combination of both the modulus as well as the conjugate. Okay, so suppose you have to find this, and we are giving Z is equals to I plus, sorry, yeah. So suppose you are getting, 2 plus I. Okay, so you write the conjugate first, so that is 2 minus I. Okay, now you will see that the sign over here has changed. Okay, but if you take the mod of it, okay, so you have 4 square, okay, and it will always be plus. Okay, and over here you have minus, so this actually becomes 4 plus. So sorry, this is 2. I directly wrote the square. Okay, so 4 plus 1 is the root of 5. Okay, so for modulus, this will always be the sum of the a square and b square. Okay, now if you take just the mod of z, you will see it actually ends up being the same as the mod of the conjugate. Okay, so you have 2 square plus 1 square, 4 plus 1 is the root of 5. Okay, so you can see that the mod of a conjugate of a complex number is actually equal to the mod or modulus of the complex number itself. Okay, so this is one thing that we can see. Now, if you remember, we had, used expression called multiplicative inverse of a non-zero complex number. Okay, and we had given it as Z inverse. Okay, we had directly, written it as 1 upon. Okay, so this is the meaning of multiplicative inverse. Okay, any complex number, if it's kind of written in the reciprocal form, you can write it in terms of a upon a squared plus b squared plus I minus b. You see, we change the sign of the of the imaginary the real coefficient of the imaginary unit. Okay, and you have a square plus b square. Okay, so if you combine these, since the denominator is the same, so you have a minus bi upon a square plus b square. Now you can see, since we already know, this is, if your z is equals to a plus ib, your conjugate of z is a minus ib, and your modulus of z is under square root a square plus b square. Okay, so if you write this in terms of your conjugate as well as your modulus, so what you get is conjugate of z upon square of the modulus. Okay, so since we are writing a square plus b square, okay, so now modulus of z is under root a square plus b square. So you square your modulus of z, you get a square plus b square. So this is how you can actually directly find the multiplicative inverse of any complex number, okay, or non-zero complex number. So if you have, so therefore z inverse, or you can write it in the simpler form. Okay. So 1 upon c is equals to conjugate of z upon square of the modulus of z. Okay, so this you can then write it as the square of the modulus of the z, okay, is actually equals to z multiplied the conjugate of z. Okay, so now let's take an example. Your z is equals to 2 plus I. Okay, what is your z inverse? Okay, so we will first find your conjugate of z, so that is 2 minus I. Find the modulus of z, so that is 2 square, 4 plus 1 is equals to root 5. Okay, and if you have your modulus of square of the modulus, you get that as 5. Therefore, z inverse is equals to, so z inverse, you have conjugate of z upon your square of the modulus. Okay, so your conjugate is 2 minus I upon 5. So this is actually 2 by 5 minus I 5. Okay, so you can find the multiplicative inverse of a non-zero complex number using either the general form that has already been given when we were trying to see the product and the quotient of the complex number, or you use this relation. Okay, so this is easier. Okay, over here, since you will have to solve the entire thing to get to the answer, it is easier because getting the conjugate of complex number is easy, as well as getting the mod of the z is easy. So you can directly use your this relation for your multiplicative finding multiplicative inverse. Okay, so let's see another example. So suppose you are given 2 root 5 plus 3i. Okay, example. So this is your z. So to find the multiplicative inverse. So z is equals to, okay, so z conjugate would be 2 root 5 minus 3i. Okay, the mod of z is in the square root 2 root 5 squared plus 3 squared. So over here, you actually get this as 4 into 5, okay, plus 9. So this is 29. Okay, and if you square the modulus of z, you get 29. Okay, so the square root sign goes away. Therefore, z inverse is equals to conjugate of z upon square of the modulus. So your conjugate is 2 root 5 minus 3i upon 29 equals to 2.5 upon 29 minus 3i upon 29. Okay, so this is your answer. Now, similarly, as we had, seen for the, when we were doing the algebraic operations, there were few rules or results or equalities that we could, prove. So let's prove some of them. Okay, so suppose the first would be that modulus of a product of a complex number, okay, of two complex numbers can easily be simplified as the product of the modulus of each of the respective complex numbers. Okay, so let's see how we can kind of prove it also. So if you take your LHS, okay, so you take your LHS part, so that is Z1, Z2. Okay, so if you take the entire product, okay, under your square root sign, so you have Z1, Z2 square. Okay, so you can write this in terms of Z1 square, Z2 square. Okay, and if you remember, we had seen before that if you have A multiplied by B under a square root, you can separate it out. Okay, so we had already done this. So now this can become Z1 square multiplied by square root of Z2 square, and that gives you Z1, Z2. Okay, so this is your RHS. You can see that this holds well when we are considering modulus of a product of two complex numbers. If you put them under modulus sign, or you multiply the modulus of each of the complex numbers. Okay, so for example, let's take 3 plus I and 2 minus 5i. Okay, so we will if you are said to find out the modulus of 3 plus I and 2 minus 5i. Okay, so instead of multiplying these first and then finding out the modulus of that, you can directly write it as 3 plus I. Mhm. Mhm. Sorry, this is 2. This is 2 minus 5i. Okay, so this will actually become the mod of 3 plus I, 3 square plus 1 square, okay, multiplied by under square root 2 square plus minus 5 square. So this becomes your 10, okay, and this will become 4 plus 25, this will be 29. Okay, now similarly as we have seen before, so you can multiply, this becomes 290. Okay, so this is what we get. Now if you want to see, okay, if we would get the same the same value if we do the longer procedure. Okay, so suppose I just first let's expand 3 plus I minus 5i. Okay, so in mod, so that will be within mod you have 6 plus 2i minus 15i minus 5i squared. Okay, so over here, since we know I squared is equals to 1, this actually becomes plus 5. So 6 plus 5, we can write it directly as 11. And over here, you have minus 13i. Okay, now modulus of this entire, this complex number would be 11 squared plus minus 13 squared. Okay, and you get that as 121 plus 169. And that again, if you add it up, you get 290. Okay, so you can see since the relation is valid on its own, you will find that whether you use the product of the modulus of the each of the complex numbers, or you find the product of the complex numbers and then find their mod, it will be the same. So similarly, another result that is given is z1 by z2 is equals to mod of z1 upon mod of z2. Okay, so this is what, let's see if we can prove this. So for the LHS, you have z1 by z2. Now, if you remember, we can write the kind of division of two complex numbers as z1 dot 1 upon z2. Okay. Now, if you take the entire thing under your square root, you have z1 square and multiplied by 1 upon z2 squared. Okay. And this you can write in terms of mod of z1. Okay. If you separate out. So let's do this step also. Okay. So you can separate out the under root multiplied by 1 upon z2 the whole square. Okay, so this you can write directly as z1 mod of z1. Okay, and this will be 1. See, the square root of 1 will be 1, obviously, and then you will have the mod of z2. And this is again, therefore, you can write this as z1 upon z2. Okay, now let's see the example. What do we get with this? So you have, you can directly write it. 3 plus I upon 2 minus 5i. Okay, so you can directly write 3 plus mod of 3 plus I and divided by mod of 2 minus 5i. Okay, and for this, then you will get 9 plus 1, and this will be 4 plus 25, and the 4 as we had got, this will be root 10 upon root 29. Okay, so you can see that this result, using this relation, you can find the modulus of the division of two complex numbers. Okay, now let's see, the different kind of results or relations that we have with conjugate. Okay, so suppose you have z1, z2, conjugate of this will actually become conjugate of z1 and z2. Okay, so for example, we can see for the examples we were using before, 3 plus I and z2 is equals to your 2 minus 5i. Okay, so sorry, not mod, we will use the conjugate over here. Yeah, so you have z1, z2, conjugate, z1, z2. Okay, so conjugate of 3 plus I multiplied by conjugate of 2 minus 5i. So that is 3 minus I multiplied by 2 plus 5i. Okay, so if you solve this, you get 6 minus 2i. You have plus 15i and minus 5i squared. Okay, so over here again, since your I squared is equals to minus 1, this becomes plus 5. So this is 11. And this would be your plus 13i. Okay, so remember before when we had found, the product of 3 plus I and 2 minus 5i. we had found it before as 11 minus 39. So you can see if we actually get the conjugate of this, this also turns out to be 11 plus 39. Okay, so you can see that this again is similar. Similarly, you can get the results. So the next one that we have is conjugate of the sum or the difference of two complex numbers will be the sum or the difference of the conjugate of the individual complex numbers. Okay, so taking the same example, let's see. So if you just, you follow the relation, let's see what do we get. Okay, so let's first take the sum. Okay, so if you take the sum, you get this as conjugate of z1 will be 3 minus I, and sum of with the conjugate of 2 minus 5i, so that will be 2 plus 5i. Okay, so this will be 5 and this will be plus 4i. Okay, so this is what we get when we do the individual. Now, if we take directly the sum of the two numbers and get the conjugate of it, so you have 3 plus I plus 2 minus 5i, and getting the entire conjugate, you can get this as 5. Over here, first it becomes minus 4i. Okay, so the conjugate is then 5 plus 4i. So you can see this relation also holds well when we are trying to see the examples of it. If we take the difference, okay, so you have conjugate of z1, so that is 3 minus I, minus the conjugate of 2 z2, so that is 2 plus 5i. Over here you get 1, this becomes minus 5. So minus 5 plus minus 5i plus I, that becomes minus 6i. Okay, let's see if what would be if we take first get the difference of the two complex numbers and then get their conjugate. So that is 3 plus I minus 2 minus 5i. Okay, we are trying to find the conjugate of the whole. So this will again be 1, and over here this is plus. So this is plus 6i, and then you will see the conjugate becomes 1 minus 6i. Okay, so this holds true. And there's one last one. Okay, so the last one, the last result that we can obtain, okay, with the in relation to the conjugate is z1 by z2. Okay, so the quotient or division will actually give you the division of the individual complex numbers. Okay, so since we have z1 is equals to 3 plus I and z2 is equals to 2 minus 5i. So let's see. Okay, so first if we find z1 by z2. Okay, so conjugate of z1 by conjugate of z2. So you have 3 minus 5i, and then you have 2 plus 5i. Okay, so again, if you find it 3i and multiplied by 1 upon 2 plus 5i. Okay, so if you remember, your z inverse is equals to conjugate of z, conjugate of the complex number upon modulus of the complex number, square of the modulus of the complex number. So, sorry, here. 3 minus I upon, okay, so your conjugate of this complex number. Okay, now this actually reverts back to your original complex number. So again, you write 2 minus 5i upon the modulus square of the modulus. Okay, so if you just find the modulus at the side, you have 4 plus 25. Obviously, that is 29. Okay, so square of this would be 29. So you can directly write it upon 29. Okay, so now you multiply your numerator. So that is 6 minus 2i minus 59. And you have then your plus 5i squared upon 29. So since we know I squared is equals to minus 1, so plus over here becomes your minus. So that is 1. And you have minus 17i upon 29. Okay. So you can see, you can try with, by yourself if you can find the same answer as this. Okay, so if you take first the quotient of Z1 by Z2 and then you find the conjugate of that result, you should get it in these terms. Okay, so for now, or maybe we can just solve it quickly and see if you do get the result. Okay, so over here we will first find only Z1 by Z2. Okay, so over here Z1, you directly write it in in this term. So you have 3 minus I, and the multiplicative inverse of we will find 2 minus 5i. Okay, sorry, this will be 3 plus I. So this is your original Z1 and this is your original Z2. Okay, now we will find the multiplicative inverse of this. So you have 3 plus I. Now this you can write, conjugate of 2 minus 5i, and then you have 2 square plus 5 square. Okay, if you directly write it in terms of this. So you have 3 plus I, this is 2 plus 5i upon 29. So you get 6. Okay, then you have plus 2i plus 15i. Okay, plus 59. Then you have plus 5i squared upon 29. Now, since we already know I squared is equals to minus 1, so this becomes minus 5. 6 minus 5, you have 1. And this is plus 17i. And then this is 29. Okay. So, I'll just continue it over here. So over here, you can see that Z1 by Z2 is equals to 1 plus 17i by 29. So now if you have to find the conjugate of this, okay, so the conjugate of the entire, this result, you get 1 minus 17i upon 29. So you can see this is equal to the answer that we got from here. So you can see that this relation act also holds good when in terms of finding the conjugate of two complex numbers divided. So for now, we will stop here. In the upcoming class, we'll see more examples where we do use the modulus as well as the conjugate of complex numbers together with the other algebraic operations. So thank you so much, and hope to see you in the next one.